Hello everyone, this is Dr. Shalini, Associate Professor, Department of Physics, R&D Engineering College. In this, we are going to look into what a wave and an oscillation is. So here, we'll be understanding the concept of the oscillatory motion, the types of the motions. Here you could make out various waves that are related to classical mechanics, electromagnetics as well as quantum mechanics. The first one we see is the sound wave, which is associated with classical mechanics. We also have the water wave relating to classical mechanics. The next is the electromagnetic waves. We also have the brain wave. And in quantum mechanics, we see the probability density waves. Also, we have the gravitational waves. Now let us look into the definition of what an oscillation refers to. It is defined as the to and fro motion of a particle about its mean equilibrium position. So it is the repeated back and forth movement. Here you could make out the tides in the sea. Here we see the back and forth movement. Also the same is observed in the movement of a simple pendulum in a clock. We have here a few definitions about what a periodic motion, oscillatory motion, time period and frequency is. If the motion of a particle of a body is such that it is present in the same direction, or it moves in a definite path in a definite interval of time, we call this as the periodic motion. We could view here a few examples of periodic motions, like motion of the earth around the sun, motion of a piston in a cylinder, motion of a ball in a bowl. We also have different types of periodic motions like oscillatory motion. In oscillatory motion, the motion of the body moves linearly with time, and in rotational or oscillatory motion, the motion of a body repeats after a regular interval of time. So a train moving in a track, a rocket launching are examples of translational motions, and the bob movement of a simple pendulum, or the beating of a heart, the movement of the earth around the sun, they are all examples of oscillatory motions. Here we just look into what an oscillatory motion is. See, if, as mentioned earlier, if the object has an oscillatory motion and if it moves to and fro along the same path in a regular periodic way, we call it as the oscillatory motion. Let us now look into what a time period and frequency of a simple harmonic motion is. So time period, in case if there is a movement of the particle, that regular interval of time is called the time period. It is given by the formula T is equal to 2 pi by omega. And the number of oscillations per second gives us the frequency for a simple harmonic motion. The frequency and time are related by the formula frequency F is equal to 1 by T. This can also be related to the angular frequency with the formula omega is equal to 2 pi by T. So just let us look into a problem that relates the frequency and period of the motion. Let us move into the problem. A particle in simple harmonic motion makes 20 complete oscillations in 5 seconds. What is its period and its frequency. As we have seen, the frequency f is the number of oscillations divided by the time period, which is 20 by 5, and it is 4 Hertz. The period t is 1 by frequency, which is 1 by 4, and gives us an answer of 0.25 seconds. Let us now look into the definition of what a simple harmonic motion refers to. A simple harmonic motion, here also we have the back and forth motion that is being produced by a restoring force. And that restoring force is directly proportional to the displacement, and it is also opposite in direction. So the displacement is given by Fs is directly proportional to x. So in general we say the restoring force is proportional to the displacement and it is in opposite direction to that of the displacement. Here we have few characteristics of simple harmonic motion. Let us look at the particle executing simple harmonic motion when it passes through the mean position and when it passes through the extreme position. At the mean position, the force does not act on the particle and its acceleration remains 0, whereas the velocity and kinetic energy is maximum and its potential energy remains 0. At the extreme position, the restoring force is maximum, its acceleration is also maximum, and the velocity and kinetic energy of the particle remains 0. Likewise, the potential energy is found to be minimum. Here we can just view into the vibration of a simple spring of a simple harmonic motion at various locations. X is equal to 0, x greater than 0 and x less than 0. We have an equation for the simple harmonic motion given by the formula x is equal to a sine omega t. So when we look into it, x denotes the displacement of a particle and it is defined as the distance from the mean position. Capital A is the amplitude and it refers to the amplitude of a particle that is vibrating in simple harmonic motion, and it is defined as its maximum displacement covered by the body on either side of the mean position. Omega is the angular frequency and it is given by the formula omega is equal to 2 pi by t. That is, omega is square root of acceleration by displacement. Next we have the time t, and the last one is the initial phase angle phi. It expresses the position and direction of motion of an oscillating particle. Let us now look in detail about the displacement x. Consider a uniform circular motion. This can be translated into linear simple harmonic motion, and we have obtained it in the form of a sinusoidal curve. So this curve, this represents the displacement x against the angular displacement theta. We know the SI unit of displacement is meter and the unit for the phase is radian. We have the initial phase angle, also called as the phase constant phi. It indicates the starting point in the simple harmonic motion. So here you could view the starting point in simple harmonic motion at time t is equal to 0. So if we have phi is equal to 0, we have the formula given by x is equal to a sine omega t. So now the simple harmonic motion is at the equilibrium position O. This is when we have this time period t to be 0 second. We have the formula for x is equal to a sine omega t plus pi by 2, and t is equal to 0 second if our displacement x is minus a. Here we have the displacement at a, and over here the displacement is at minus a. We have the formula given by x is equal to minus a cos omega t. Whereas when the amplitude is plus a, we had x is equal to a cos omega t, and for the amplitude minus a, we have x is equal to minus a cos omega t. And when the displacement is at 0, the equation is given by x is equal to minus a sine omega t. These are the equations for velocity, acceleration, kinetic energy, and the potential energy. We have explained in detail the values of the potential velocity v. It gives the value a omega cos omega t plus phi. So when the velocity is maximum, we have v max is equal to a omega. The value of cos omega t plus phi remains 1. Coming into acceleration, it is given by the formula a is equal to minus a omega square sine omega t plus phi. Whereas the maximum acceleration is obtained by giving the value of sine omega t plus phi to be equal to minus 1, and we get the maximum acceleration to be equal to a omega square. We also have the potential energy and the kinetic energy, which are the energies in simple harmonic motion, which gives the value of u is equal to half m omega square x square, and k is equal to half m omega square a square minus x square. So when we go with the total energy, we have E is equal to half m omega square a square. Let us now look into few problems that relates to the period of a spring. So in physics class, a student measures that it takes 18.1 seconds for an oscillating spring to complete 15 cycles. What is the period and frequency of the spring? We have the formula for time period given by time divided by cycles. We get an answer of 1.21, and the frequency to be equal to 0.83 Hertz. Coming into the second problem, what is the period and frequency of an oscillating spring K is equal to 10 Newton per meter with a 200 gram mass attached to it? T is equal to 2 pi square root of m by k. Substituting the value of m to be equal to 200 gram, this on conversion to kg becomes 0.2 kg. We have the value for k given by k equal to 10 Newton per meter. On substituting these values in the given formula, we get an answer of t to be equal to 0.89 seconds, and the frequency, which is 1 by t, gives us an answer of 1.3 Hertz. Coming to the next problem, a child in buoyancy swing is suspended from a spring. If the spring stretches 15 centimeter, when the 8.5 kg child is put in it, what is its spring constant? How much time does it take for the child to complete one bounce? We go with the same formula. T is equal to 2 pi square root of m by k. On the substitutions of the value of m to be 8.5 kg and k to be 556 Newton per meter, we arrive at an answer of t is equal to 0.78 seconds. An object at the end of a spring oscillates with a period of 1.85 seconds. If the mass of the object is 1.5 kg, what is the spring constant of the spring? We have the value of K given by 4 pi square m by t square. On substitution of these data of m and t, we arrive at the value of K to be equal to 17.3 Newton per meter. Thank you.